Okay, today we're going to be looking at the concept of load matching. So, if we want to get the maximum power output from a circuit, we need to match the load and internal resistance. Now it's important to note here that if the load resistance and the internal resistance are the same, you'll get the maximum power out of your circuit. But you may not want to run a circuit at its maximum power because that is not going to be the most efficient circuit, and we'll end on what the most efficient circuit is. But this is matching the load and internal resistance gives you the maximum power. So we're going to look at this circuit. So this is our internal resistance, little r, and it's just going to be 1 ohm. And here's our voltage. So this is our cell. And that's a 10-volt battery. And it's just connected to a little lamp here. Now, let's have a look at, well, the value of the internal resistance remains constant, but what if we change the resistance of the lamp? And then we want to look at what is the total resistance of the whole circuit. So this is our total resistance. And when the resistance of the circuit is given here, this is the voltage over the lamp. So if we were to put a little voltmeter here, this would be the readings you would get across the lamp as the resistance over the lamp increases. So we can then use the voltage of the lamp using V equals IR, and we can calculate the current in the circuit. And we can also use one of our equations for power, I squared R, to give us the power in the lamp. So what we see here is if you look at the value for when the internal resistance and the resistance of the lamp are the same, so it's 2 ohms, we get the maximum power in the circuit. However, if we look here, we also get the current's also quite high. It's not as high as this one, but it's still quite high, and that's not always desirable. So we know that in a real circuit, the internal resistance is going to be incredibly small, and therefore to match it, the current must be very, very high. And we can see that in the table. We can see this is quite high values for the current. The resistance of the lamp is not going to be as small as 1 ohm, so this lamp isn't going to have a resistance of just 1 ohm. So this circuit is not really, it's in reality, it's not this. You wouldn't have this circuit of a 1 ohm lamp. So how do we get round this little problem? So in real circuits, what we would do is we'll draw another circuit. So we've got our little resistance R, we've got our battery, we've got our R load. We're going to, instead of having a lamp here, we're just going to have our load, and this we've put a resistor in here, but this could be any component. It could be a motor, it could be a lamp, it could be anything. And what we do is, in a real circuit, we can then add another resistance in to help us with our load matching. So this is R extra. So our battery is the same, it's R is still 1 ohm and it's still 10 volts. Now we know that because I equals V over R, if we increase the resistance, we decrease the current. So this is why we've put this extra resistance in, so we have a smaller current. Because if we saw previously on our other table, just bring the other table back up, we were dealing with currents of, when we had our situation where we'd load matched the internal resistance to the lamp resistance, we had a current of 5 amps. Now if your computer had a 5 amp current going through it, would burn it out completely. So 5 amps is quite a big current. So by increasing the resistance, we can decrease the current, and we can control the current going through whichever device we have here, and we can protect that device from having too high a current, because that can be dangerous. It can get really hot, it can be a fire hazard, or it can just break your device. So let's look at what happens in this situation. So here we've got, instead of just having our internal resistance, we're internal resistance plus this extra resistance. So now this is a lot higher. It's sitting at 100, that's why we picked 99. And our load resistance, so here we're going to change through a number of different values. And our total resistance is these two values added together. Now you can see the voltage over our device is given by 3 all these values here, and our current, note here, this is in milliamps, so we have reduced the current significantly from what it was previously. And now we have this is our power is in milliwatts as well, so the power is also a lot less. So there's two reasons a circuit designer would do this. Use an extra resistor. The reasons would be, first, higher resistance components can be load matched. So we said previously our lamp would not have a resistance of 1 ohm. A component is more likely to have these kind of values for resistance. So by having our extra resistance and load matching to R plus R extra, we can now load match to components that have a higher resistance. Because if we see, when we have our 100, 100, we still have our power in the component is still at its peak when we load match to the resistance between R and R extra. Secondly, if the extra resistance is significantly higher than the internal resistance, the circuit operation is no longer dependent on the internal resistor, since the matching of the extra resistance is more important. So you can just ignore the internal resistance of your power source in that situation. Now, as I said at the beginning, it's important to remember that the maximum power transfer does not occur when the circuit is at its most efficient. So maximum efficiency occurs when load to source resistance is high. So the ratio of load to source resistance is as high as possible. That's when you're going to get your most efficient circuit, and often that is the situation that you're seeking to attain, is to increase efficiency and not always your power. So I hope that helps.